next is to show you how you can evaluate, do one more integral just to show you how these singularities are handled, and this is a famous integral, it is called the Derrick integral. It is one of the Derrick integrals, and it is the following. It is integral 0 to infinity dx sin x over x. This integral. Okay. This integral happens to be finite. This definite integral happens to be finite. It is not absolutely integrable, because if you took the modulus out here, if you took the modulus, then this sign is always positive, mod sign is always positive, and the term and this function being bounded, the integrand is disappearing, is decaying like 1 over x, and of course dx over x diverges logarithmically at infinity. So this integral is not absolutely convergent. There is no problem at the origin, because this thing here goes to 1 at the origin, so there is no singularity at the origin, it is a removable singularity. But at infinity you have a problem if you took absolute values. On the other hand, it turns out that because sin x changes sign, becomes positive and negative, in the limit the contributions will actually see to it that the whole integral is finite. The positive and negative contributions adjust themselves, cancel each other in such a way that the answer is actually finite. Because if you plot this function, it is actually this sin x over x, it periodically vanishes, it does this, and this envelope is going like 1 over x, but these positive and negative contributions add up to give you a finite answer. And what is the value of this integral? It is pi over 2. Actually it turns out that if I multiply this by a constant, let us call it b, some positive constant b, the answer remains pi over 2, it does not change for all values independent of b. And the reason is very simple, you can actually put bx equal to x prime if you like, and then dx over x is the same as dx prime over x prime, so the whole thing becomes independent of b, because the limits of integration remain unchanged. So for all positive values of b, the integral is pi over 2, and for all negative values of b, it is minus pi over 2, because sin bx is then a negative quantity, minus sin mod bx. So this is pi by 2 mod b, the sine of b, or b over mod b is a better way of writing it. So it is a discontinuous function plotted as a function of b. For negative values it is minus pi over 2, and then it jumps discontinuously to plus pi over 2. So it is one of these famous discontinuous integrals, and from this integral you can derive a very large number of other integrals. What I would like to do is to derive this, by the way this result is easily derived from elementary considerations, but I would like to derive it using contour integration, and here is how you do it. The first thing to note is to write that that this is an odd even function. So write this as half integral minus infinity to infinity dx sin bx over x, right, in this fashion. Okay. Now we are laying the groundwork for trying to get a closed contour somewhere. But you see the difficulty with this sign is that right away you can see what I am going to do is to have an integral along the real axis, I am going to try to close it in the upper half plane or lower half plane, get a closed contour value, and then try to argue that the contribution from that semicircle vanishes. But I am in trouble, because the sin bx is e to the ibx plus e to the minus ibx. So if x becomes z and has a positive real imaginary part, then one of those two exponentials blows up in the upper half plane, the other one blows up in the lower half plane. So I can't work with sign, I can't do that at all. Instead what I do is to say this is equal to half the imaginary part of minus infinity to infinity dx e to the ibx over x, imaginary part. Yes. But you got to be a little careful here. By writing this I have actually got into trouble, because at x equal to 0 I am in trouble. here. It is true I take the imaginary part, I get sine, it cancels. But the moment I write this integral itself makes no sense because at the origin it blows up, it is not integrable at all. So I need to be a little cautious about this. What I do is the following, I consider the following line integral. Consider integral over a contour which I am going to specify, contour Z, dz e to the I bz over z over the following contour. In the complex z plane, this contour runs along from some minus r to some plus r in this fashion, starts here, runs along here, and then because this is singular at z equal to 0, I avoid this singularity by going around it, make an indentation in the contour, go around it and go all the way to plus r, and then close the contour with the semicircle in this direction. That is my total closed contour C. Okay. This is an entire function. This has got a simple pole at z equal to 0. So this whole integrand has a simple singularity, simple pole at z equal to 0, but that is outside my contour. This is a closed contour which lies entirely in the region of analyticity of the integrand, and by Cauchy's theorem this integral is 0. So I start by saying 0 equal to this guy, and now I write this out piece by piece. This is equal to an integral from minus r to this point, so let us call it minus epsilon, this is epsilon, minus epsilon dx, because remember on the real axis z is x, dz is dx, e to the I bx over x plus an integral from epsilon to r dx e to the I dx over x plus an integral from here to here around this contour. But what is z on this contour? On this contour z equal to epsilon e to the I theta, where epsilon is an infinitesimal positive number. So dz is going to be epsilon e to the I theta I d theta. What is the range of integration of theta? I start here and go there. I start at pi and go to 0, the other direction, right. So that is important. It starts at pi and goes to 0, this fashion. And then e to the I be epsilon e to the I theta divided by epsilon e to the I theta. Okay. Notice how this epsilon e to the I theta cancels out obligingly. And I can go to the limit, epsilon goes to 0, and then this fellow just goes to 1 out here, and the answer is just minus I pi. So this little infinitesimal portion cannot be neglected, it gives me a contribution minus I pi. You have got to keep it carefully. Plus there is a contribution from this large semicircle on which z is r e to the I theta, I d theta, divided by r e to the I theta, is this e to the I b r e to the I theta. And this integral runs, this theta runs from 0 to pi, this fashion. Okay. So 0 equal to that huge sum out there. Now this thing here, minus r to r with a symmetric neighborhood left out between minus and epsilon is called the Cauchy principal value integral. So the Cauchy principal value is defined. If there is a singularity on the line of integration and a symmetric neighborhood of this is left out, an infinitesimal symmetric neighborhood is left out, what you get is a principal value integral. So this is equal to principal value integral minus r to r dx e to the I bx over x. This thing, this p stands for the Cauchy principal value. A little later when we look at dispersion relations, we will see the use of this concept here. But right now it is completely rigorous. This integral exists and there is no question about it. It avoids the singularity, and then this portion, I am going to go to the limit in which epsilon goes to 0, so I might as well write it out directly. This is minus I pi, okay. And then this portion here, this portion cancels against that, and you see as long as you are in the upper half plane, it means z has a positive imaginary part with a very large r there, and then the positive imaginary part gives you, because of that factor r, gives you a damped exponential which goes to 0 in the limit as r goes to infinity. So we could write this contour integral in the limit r goes to infinity, tells you that limit r tends to infinity, principal value minus r to r dx e to the I dx over x is equal to I pi, because this contribution goes to 0. Take imaginary parts on both sides. Equate imaginary parts. It says principal value integral minus limit. By the way, limit r goes to infinity minus r to r is the same as minus infinity to infinity, it's just shorthand for that. So principal value minus infinity to infinity dx sine bx over x equal to pi. But there is no singularity in this at x equal to 0 in the imaginary part. So I do not need that, it is the same as the integral itself. Okay. And this is an odd function. So 0 to infinity is pi over 2. I used the fact that b was positive because I closed it in the upper half plane and said this contribution went to 0 because of this factor e to the I b z. That is only true if b is positive. So this means this is true for b greater than 0. For b less than 0 I take out the minus sign first and then it is the same integral with a minus sign. Okay. So this has actually told us this value of this discontinuous integral. So notice how I used contour integration to avoid this singularity, add this well chosen 0 here, close the contour and use Cauchy's integral formula, integral theorem, to evaluate the integral, that a real integral that I needed. So you can see from this example the power of this method, provided you use it carefully and cautiously, it actually gives you very, very powerful results. This particular integral can be evaluated by elementary means actually, as I said, but it still illustrates to you exactly how such integrals are to be handled. I could have done this by enclosing this in this fashion also, could have done that, nothing to stop me, but now the value of the integral is not 0, it is equal to 2 pi I times the residue at this point. So I would not have got 0 on the left hand side, I would have got some finite answer, but this contribution itself would have changed in sign because it is now pi to 2 pi. So it would have become a plus I pi here, and it would give you exactly the same result as before. So you could have closed it in either plane. I could have started with e to the minus I bx and closed it in the lower half plane and indented it either way you like, etc. Does not matter, provided you do it properly, you are guaranteed to get this answer. It is quite unique, this answer. By the way, once you have this answer, then you can actually do many other things with it. You can also differentiate this, you can integrate this, etc., over b from 0 to some c, and when you do that you are going to get an integral 1 minus cos x divided by x squared. That too is finite. So a whole sequence of singular integrals can be read off from this single answer here. I will give that as an exercise to you to check out. So let me stop here. We will come back to this. We will come back to this little trick here when we derive dispersion relations for physical response functions, etc. Okay, so let me stop here today and then we take it from this point next time. By the way, I thought of another little point in answer to this question that was asked about what is the physical meaning of this residue. But the thing is, it depends on the application, depends on what the application is. One common application would be that we will discover that response functions to various stimuli will turn out to be dependent on the frequency with which the stimulus is applied. So what we will do is take a general function which is a stimulus, a force acting on a system, Fourier transform it into frequency components, and then look at the response in linear response component by component. Then it will turn out that the response function has singularities in the frequency as a function of frequency whenever the system undergoes a resonance, as you expect. If you look at an oscillator and you push this oscillator with exactly the resonant natural frequency of this oscillator, you know there is a resonance that is going to appear. So a divergence will appear at the resonance frequency. Okay. Now the residue, and this will typically turn up in the response function, in the susceptibility, frequency dependent susceptibility, it will turn up as a pole of some kind. Then the residue at that pole will give you the strength of this response, in some sense the strength of this particular natural frequency. What will be the contribution from this natural frequency to this response of the system as a whole. As you know, most physical systems are not simple harmonic oscillators, there are many natural frequencies, and at each time, each distinct natural frequency, there would be, if it is a discrete spectrum, you would have poles in some susceptibility, and the corresponding residues would give you the strengths with which this response occurs, and they need not all be equal to each other. So that is one way of seeing what this residue is. It is acting like some kind of coupling oscillator strength, if you like. There are other issues, there are other contexts in which you will see, as we do some more examples, you will see what the residue looks like in various cases. So there is no simple answer to single answer, obviously it is to what does it actually physically correspond to, but it depends on the physical application. We will see. So I thought I would mention that here. We will next do very rapidly linear response theory, and then I will explain the analytic properties of the susceptibility itself as a function of the frequency, and then things will become a little clearer. Yeah.
So what do you mean by a function is singular at a point? You told yesterday that it's not that the function blows up at that point. So what do you really mean by that?
So far the singularities we have looked at are poles, and at a pole an analytic function is divergent, it is infinite, it blows up at that point. We will subsequently come across other singularities called branch points, where the function need not blow up, but the function would be multiple valued, and those values would coincide at some special point, and they are called branch points. And at those points the function is not analytic, you cannot do a Taylor series, but the function does not blow up at that point. We have not come across those singularities as yet.
Like the Riemann surface after.
Oh yes, absolutely. So for such functions, it will turn out that a single copy of the complex plane is not sufficient. In order for me to produce a single valued function, I need to take several surfaces and paste them together in a specific way to form what is called a Riemann surface for the function. And this multiple sheeted structure, the function will be single valued at every point. Yeah. So we will see that in detail, we will understand. Yeah. Incidentally, there are other kinds of singularities which I did not talk about, the many other kinds of singularities. We talked about essential singularities, but even the example that I talked about here, namely this 1 over sine pi z, which has poles at all the integers, you could ask what is the nature of the singularity at infinity. Well, if it is just e to the power z, then I know it is an entire function, no singularities in the finite part of the plane, and I also know e to the z is not a constant, it is a function of z. Therefore, it must be singular at infinity. The question is what sort of singularity? Well, I can bring the point at infinity to the origin by changing from z to w equal to 1 over z. Then this function looks like e to the 1 over w in the w plane, and that has an essential singularity at the origin. So I conclude that e to the z has an essential singularity at z equal to infinity. Now you could ask, what kind of singularity does 1 over sine pi z have, which has a pole at 0, at 1, 2, 3 and minus 1, minus 2, minus 3 etc. What does it do at infinity? Well, these poles go to an accumulation point. You must ask, what do they do actually in the Riemann sphere, on the Riemann sphere? And on the Riemann sphere, if you recall, the positive real axis corresponded to 0 longitude, the negative real axis corresponded to 180 longitude on the other side. Now you are saying that at 0 there is a pole, so there is a pole sitting here, and then there is a pole at z equal to pi, and then 2 pi, it is z equal to 1, 2, 3 etc. etc. So those guys would be poles sitting here and then here, 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 here etc. till you approach this, and similarly there would be poles here, and they are getting closer and closer as you approach the point at infinity. Okay. So what you have here at the point at infinity on the Riemann sphere is not a simple pole, it is an accumulation point of poles. It is no longer an isolated singularity, because if you get arbitrarily close to it, there are then many poles which are getting accumulated, infinite number of them are joining up at the point at infinity. So that is a difficult singularity, it is an accumulation point of poles. Okay. So you can have very hairy objects like this, very complicated looking singularities at infinity, but most of the time the functions that we deal with, we will deal with functions which are multiple valued and for which you have to define a suitable Riemann surface etc. So we will do that carefully, we will take care of it. But all the functions we have used so far are meromorphic, they have got a finite number of poles or an infinite number of poles, but we are not we are dealing with contours which have enclosed a finite number of poles, no limit points etc. etc. Okay. We are only dealing with these examples, but we will come across more complicated examples as we go along. Okay. Now one question that arises naturally is, suppose you are given a function whose only singularities in the finite part of the complex plane are poles of whatever order. Such a function is called a meromorphic function. In the finite part of the complex plane, this function has at best only poles, might have no singularities at all, in which case it is an entire function, but it could have poles, in which case it is a meromorphic function. And the next question that arises is, can we write in the neighborhood of a pole, of course, for a meromorphic function, you could write this function as a singular part which involves negative powers of z minus a, where a is the position of the pole, and then a regular part. But one could ask, suppose I tell you all the positions of all the poles and I tell you what the singular parts are, then can we represent the function in terms of its singular part plus some portion which is regular? And the answer is yes. It turns out that for meromorphic functions you can write the function down everywhere in the complex plane as the sum of a singular part plus an entire function, which of course has a singularity. It could either be a constant or has a singularity only at infinity. And the classic case, of course, if it has got just a finite number of poles like 1 over z minus 1 plus 1 over z minus 2 or something like that, that is it. This is already such a representation. But if it has an infinite number of poles, then questions about convergence appear. And the classic example of such a representation, which by the way is called a Mittag-Leffler representation, or series if you like. The classic example of this is the function cotangent of pi z. So let us see how that can be derived. There are several ways of doing so, but I am going to sort of work backwards from a result which you already know. And the result which we have already used or derived is the following. Remember, we showed that the sum from n equal to 1 to infinity 1 over n squared plus a squared was equal to this famous Langevin function cot hyperbolic pi a minus 1 over pi a, and I said a was a positive constant or a real constant, so that this did not blow up at any point. Okay. On the other hand, regarded as functions of a, both sides are analytic apart from some singularities on either side, and certainly one can continue this, and we are going to talk about analytic continuation in detail. We are going to write this, we can write this expression down as a functional relation between two functions of a, this quantity a. So you could make a complex variable, and then you can equate these two sides by this permanence of such equations, functional equations. So let us do that. Let me set a equal to I times some complex variable z, say. Then this immediately becomes pi over 2 I z cot hyperbolic pi I pi z minus, well, the pi cancels, so 1 over 2 a squared 1 over 2 z squared, but then because it is an I there, I squared, it is minus 1, so that goes away. This quantity must be equal to summation n equal to 1 to infinity 1 over n squared minus z squared, because a squared is minus z squared here. Now wherever these two functions on either side make sense, this equality is valid. Now but what is this quantity? It is cosh divided by sinh, and that is equal to, on the numerator you are going to get cos, and in the denominator you are going to get an I sine pi z. So it becomes, the whole thing becomes minus I. So let us write this out. It is minus I pi cot pi z divided by 2 I z plus 1 over 2 z squared equal to summation n equal to 1 to infinity 1 over n squared minus z squared. So let us solve this for cot, and then this I goes away on both sides, and I get minus pi cot pi z, I multiply by 2z, so this is plus 1 over z equal to twice summation n equal to 1 to infinity z over n squared minus z squared, and there was a minus there, so I want to get rid of that. So I will write cot pi z equal to pi cot pi z. So this becomes a minus, it becomes a plus on this side, plus twice summation n equal to 1 to infinity z over z squared minus n squared. So I will absorb the minus sign there in this place. Okay. So that is a representation for cot pi z. Now what are the properties that we know about this cotangent? We know that it is cos over sine, and therefore since cos and sine are both entire functions, we know that this function has simple poles at all the integer values of z, including 0, and this makes it explicit out here. You can see that this function here, it is z plus n times z minus n, so at all the non-zero integers there are simple poles, and then the pole at 0 appears in this function here, out here. So this almost looks like such a representation, that it is essentially equal to, if you like, a sum over poles. But this Mittag-Leffler representation should isolate all the poles. So you have no business to write it as 1 over z squared minus z squared. You should really write it as the pole part and sum over all the poles explicitly, right. So the way to do that is very obvious. This is equal to 1 over z plus summation n equal to 1 to infinity. If I write this as 1 over z minus n plus 1 over z plus n, then of course the numerator is 2z and the denominator is this guy here. Okay. And now one is tempted to say, aha, this summation 1 to infinity z plus n, I will change n to minus n, and then of course it becomes 1 over z minus n, but n is going to run now from minus infinity to minus 1. So it looks like we are almost there. This is a sum over the poles at all the positive integers, this is sum over the poles at all the negative integers, and this is the pole at z equal to 0. This looks like such a representation, but not quite, because it is clear that it is not such a representation unless I can write this sum and this sum separately as two separate sums. Only then would it be a sum over all the poles individually. On the other hand, such a sum will diverge, because if I just remove this and write 1 over z minus n, then this goes like 1 over n, and therefore it blows up logarithmically, goes all the way to infinity, and the series is not convergent. Similarly, this series too is not convergent. In other words, I am not allowed to take the square bracket and separate the summands and write it as two different sums. So here is a case where you have to first sum these two terms inside the square bracket for each n, and then do the summation over values of n. Is that clear? Because of convergence problems. How do we get rid of it? Very, very easily. What does this thing do as n becomes very large? It goes to minus 1 over n, and this goes to 1 over n, plus 1 over n. So let us simply rewrite this as 1 over z plus summation n equal to 1 to infinity 1 over z minus n plus 1 over n minus 1 over n. So plus 1 over n plus 1 over z plus n minus 1 over n. That is perfectly legitimate. All I do is to add and subtract 1 over n on either side. But this portion can be summed separately, because the asymptotic behavior of this for large n, the 1 over n part cancels and the next term is proportional to 1 over n squared. So this summand goes like 1 over n squared and therefore is convergent all the way to infinity, and ditto for this portion here. Okay. So we immediately have achieved what we wanted. We have pi cot pi z equal to 1 over z plus summation n equal to 1 to infinity 1 over z minus n plus 1 over n in this fashion, plus a sum 1 to infinity this guy, but I can change n to minus n in that sum, and it then becomes equal to this on this side. Therefore, this summation is n equal to minus infinity to infinity, with a prime here to show that n equal to 0 is out here. It is not included in this sum. And of course, if I put n equal to 0 inside this summand, then this goes away and you just get a 1 over z out here. On the other hand, you got to be very careful. If you put z equal to 0, this thing cancels here. So you could take this inside and just write it as an unrestricted sum minus infinity to infinity. So the whole thing just becomes this. Is that correct? Did I say something? I would rather do that. Yeah, I'd rather leave it like that. 1 over z plus a prime, because maybe saying something which requires better examination. Okay, whatever. But this is explicit now. It says that all that cotangent of pi z, pi cot pi z, is a meromorphic function. It has only poles in the finite part of the plane. It has poles at all the integer values of z, and those pole pieces are all sitting here. Every one of them is sitting here. This portion is not singular, but it is necessary for you to write such a representation. Okay. In fact, the most general way of writing a meromorphic function, the Mittag-Leffler representation, would be to write it as a sum over the singular terms plus a portion which will ensure convergence, which could in general be z dependent itself, plus an entire function outside. But in the case of cotangent, that entire function portion is missing, it is not there, and this part alone, this function here which regularizes this series, is a constant, doesn't happen to so happens it does not depend on Z, okay. But it is all the same, it is a Metag-Leffler genuine representation. So this example shows you got to be a little careful in writing it, even though it looks like you have got this here, it is not the representation, and this is not either. If you remove this, you need to put this extra piece here in order to do this, okay. So we work backwards from this Langevin function to get that, but you can also start from a different viewpoint and go back and derive this relation here. Now an interesting thing emerges immediately. If you differentiate both sides with respect to Z, then this side becomes pi squared over sine squared pi Z, differentiate cotangent with a minus sign, but the minus sign I am going to kill out here, and what happens is this becomes a minus 1 over Z squared, and this becomes minus 1 over Z minus n whole squared. That does not get differentiated. And now you can add the n equal to 0 term also along with this, and this therefore becomes equal to summation n equal to minus infinity to infinity 1 over Z minus n whole squared. I want you to be surprised by this relation. It is a remarkable relation, because here are algebraic functions Z minus n whole squared. This has a double pole at all the integers including 0, and it is just a sum over those double pole terms and nothing else, and that turns out to be a sine function, a cosecant function like. So this series here is the starting point, this or that is the starting point for a large number of other developments in this, but you can see how complex variables enables you to get hold of such powerful representations. Here is something which is trigonometric on the left hand side, a transcendental function, right hand side is just a sum of rational functions, and the two are exactly equal to each other. So this formula you should ponder over it for a while, see how remarkable this formula is. There are many other such instances, and they lead to what are called Eisenstein series. They emerge from this. This is one starting point for such developments.